Rates of reaction. Chemical kinetics is the branch of chemistry concerned with rates of chemical reaction, so how they consume or increase. So reaction rate is the change in concentration of either a reactant or a product of a chemical reaction per unit time. There'll be a unique unit time for this stuff. So measuring reaction rates, there's many different ways that you can do this. You could do this using a syringe and calculating the volume. You could do a mass using the balance. You could do it with a measured color change over time. You could use a pH meter. You could even connect up an electrical conductivity device. These are all ways of measuring reaction rates. But we want to calculate some average reaction rates to start with. So this is going to be the change in a reactant or product concentration over a given interval of time. It's essentially what we're doing here is we are doing the slope. So we've got, kind of y2 and our x and our y values. Okay, so we've got sort of 4 points that we are going to be subtracting. So there it is. Now, we also might see it as a change in concentration over change in time. They mean the same thing, and essentially it's y2 minus y1, x2 minus x1. And our units are going to be in moles per liters times seconds. So this is actually your concentration right here, right? That would be your concentration from the liquid section of last year, and then there's your time unit. So the average rate of reaction can be calculated in two ways. We can look at how reactants disappear, or we can look at how products are forming. And so here's another example of that. In our first slide, we have all reactant A, and you can see over 40 seconds, the red is being converted into blue, and we even have some concentrations here. And since we have a time, we could go about and start to do some calculations with increasing and decreasing reactants and products. All right, let's take a look at an example. In this example, we are synthesizing water. So we need to understand what our reactants and products are doing. In this reaction, our hydrogen gas is going down, our oxygen gas is going down as this reaction proceeds. And that must mean our our water is going up. So that's going to be important for our sign. So what is the production of water for this reaction if the concentration changes from, maybe concentration of water is a weird way to do it, but we'll go with it. And we have our time here. So the first thing you need to do is simply write down your equation. So we're going to be taking our second concentration and subtracting off our first. So there is our first and there is our second. So this rate is with respect to water. So here I've gone ahead and plugged my points in. So there's my second point and there's my first point. And of course, there's my time. You grab out your old calculator, you get 2.67 times 10 to the minus 3 moles per liter times seconds. Now a little note here that we are producing water, so we actually have a natural positive sign on this answer, and that's fine. Well, what happens if we flip this around? What if we make this the decomposition of water? All right, so same things here. Of course, now water is decreasing. And so I flipped the concentrations around just to make this sense because the water's concentration is decreasing, if that would be possible. So there's our equation. We're after water again, and I have flipped our signs. Now, mathematically, we're going to get a negative up top here, and a negative isn't going to make much sense with respect to our disappearance of water. So what's done is there's another negative inserted here. And really the point is that two negatives are going to make a positive, so we get a positive answer. These rates, everything has to be positive. Negatives won't make sense. Whether things are appearing or disappearing, it needs to be positive, so just be wary of that. So two negatives will make a positive here. Now, graphing this is one thing that you can do. So if you're given a graph, and this would be a decreasing one here, what happens is you'll be given two time intervals, 2 points, here and here, and you're going to need to do this, well, make it look like slope essentially. So you're going to find your, your rise and your run, if you will. So if you've got a graph, you really just need to pick 2 points on your curve and you can go ahead and figure out what the values are going to be. Sometimes there's a table of values given, like in this next question, and that makes it much easier. But if you don't have the table of values, you can just interpret the information off the graph. So here is a reaction, and you can see that we've got here is the reactant we're dealing with. You'll notice our concentrations are decreasing as time goes on here. That's fine. So if you wanted to plot this, there's your time on the bottom, and there's your concentration, and there is your disappearance rate. So what's indicated on here is we've got what's going on at 300 to 400 seconds. So you got your 300 seconds, you got your 400 seconds, you make your rise, you make your run, and you start to read off the values. So you get your values that are going to make up your 2 points. So here it is. There's determined from 300 to 400. It's change of y over change in x. And again, you can just kind of look to the data over here, and you can label these as, there's x1, x2, y1, and y2, and then just go over here and plug your values in, y2 minus y1, and so on. And you get a very small answer for that one. So that's what happens if you have to do a calculation from a table of values or from a graph. Just find 2 points and go ahead and do this. Now, instantaneous is just slightly different, but very similar. So we're given a specific time, and what we want to do is the slope of the tangent on the concentration graph. So for this question per se, the question was saying at this exact time right here, I'm trying to do it in purple, there it is, so it shows up. It's saying what was the concentration of our hydrogen peroxide. So you don't have 2 points, but you still do the same thing. You draw your tangent line in. It's going to be the hypotenuse, and then you find your values for your rises and your runs, and you go from there. And I just drew it freehand, so forgive me for that. So instantaneous rate of reaction. So let's get the instantaneous rate of reaction of oxygen at 5 seconds. Here is our balanced equation, and here is our graph. So we're just after oxygen in this example. So first thing I want to do is it's at 5 seconds. So at 5 seconds, which is about right here at the green line, okay, there's about 5 seconds. We'll draw our tangent line in, make it as long as you want, do the best you can, and then it's about getting your values here. So we're at 0.1 and 0, and then you can kind of get these values here, and I've sort of just gone ahead. So how much time is elapsing? It looks like we got about 10 seconds elapsing, give or take. And in terms of figuring out this value for concentration, go across, it's about 0.15. So using the 10 and the 0.15, all you need to do is you say, again, it's our x over our y's. So there is my y1, or sorry, there's my y2, and there's my y1. Again, that value and that value. And then we've got about 10 and 0 going on here. So those are those two values. And then there's your concentration for that. So again, it's just a matter of doing the slope. Here's another example. This one's sort of already developed here. So if we look at the red triangle, again, we've got our instantaneous point right here. And so what we need to do is we need to find how much time had elapsed, which happens to also be 10 seconds. And then we need to figure out our concentrations. So it's just a matter of kind of going across and figuring out what the values are going to be at those endpoints. And then there is a calculation. I sort of drew over it there. And then down to the green triangle, the same thing we've got going on. We've got an instantaneous point of, looks like it's right here. So again, we had our values figured out. And you can double check those if you don't believe me. So again, your triangle was drawn, and you go ahead and you get your time, and you get your concentration, and then you're just plugging it into that equation. So there's just another example of how to do it for the instantaneous. There's a final way of doing this, and that's using the balanced equation. So here is your balanced equation. Now this is going to look a little funny at first, but don't be intimidated. So again, the lowercase is just standing for your coefficients. So if you want to figure out the rate, now again, we're going to have some pluses and minuses because we've got some reactants, right? So these reactants are going to be decreasing and the products are going to be increasing as a reaction. So the first thing you want to do is, for your A, you'll notice that we put the coefficient on the bottom, and whatever your values are going to be, a concentration number you can put in there. And there is a minus sign, and the minus sign is because it's a reactant and it's decreasing. And you can compare that to B, and it'll be exactly the same. Again, B is a reactant. Again, we have our minus. Again, we have our coefficient here. And you can compare that to C and D, and the only difference between the C and D is that they are positive because they're increasing as this reaction continues. So that's what it kind of looks like. Now we can put this into an example, and again, you can compare any of these you want when you're doing a question. So let's consider the following reaction. We've got dinitrogen pentaoxide there, and it's creating nitrogen dioxide and oxygen gas. So there's two ways to represent this reaction. In terms of the disappearance of the reactant, right? This one disappearing, or in terms of the production of the nitrogen, or even in terms of the production of the oxygen. So those would be increasing. So there is our balanced equation. So let's sort of set this up. So for every 1 mole of O2, again, notice there's a 1 in front, we've got 4 moles of NO2 are being produced. Okay, so we could compare those. So this means the rate of production is 4 times that of the oxygen, right? Because there's a 4 in front of the nitrogen dioxide. Therefore, the rate production of O2 is 1/4 the rate of production of NO2. So you can express this rate as the following. And if you wanted to express it the other way around, you'd of course have a different ratio. And don't forget that there's all positives in here because we are producing something. Now we can look at the flip side here with our reactant. So we've got 1 mole of O2 produced from 2 moles of the N2O5. Okay, comparing those, you see it's half, and then that's going to be our relationship. So you'll notice that we have a negative sign here because the reactant is what we're talking about. That's what we're comparing, and it's going down. So so notice the expression involving the NO2 reactant has a negative. This is essentially what I was just kind of explaining here. You got your change in concentration as your final minus your initial. And by convention, we're after a positive value. So you got it in the end, and it's saying multiply by -1 here. And that's kind of what we did on the earlier slide. Bottom line is all your answers need to be positive. So do what you need to do to make a positive in the end. Take a negative, make it positive. And those are the two we were talking about, right? Okay, so here's finally a question based on the same equation, and it is saying at 90 seconds. Now the 90 seconds is kind of redundant information because we're just looking about the rates at that 90 seconds. So firstly, we want to determine the rate of the appearance of O2, and we want to determine the rate of disappearance of the N2O5. So we can kind of use those rates that we just came up with in the previous question. There's our balanced equation. Move that to the top. So 1 mole, 1:4 is our ratio. So that's what we're going to use when we actually come up with this rate. And all we're going to do is we're going to say the rate of production of the O2 is equal to that 1/4 and multiplied by that value that was given in the question. And there you go. That is your answer. So it's just using these fractions, or perhaps they're fractions and not necessarily a fraction. Could be a whole number. All depends. So for the last one here, we've got 4 moles of the NO2 produced for every 2 moles of the N2O that's decomposing. And so this is a rate we can simplify a little bit. So it's 2/4 or a half. So if we want to find the formation of this one, there's your 1/2. And again, there's your value in the question because it's at 90 seconds. And there would be your answer. Notice no negatives involved here. It is all positive stuff.